Hello and welcome to Physics 1D Forces Review. So we are going to start off considering a cart on a frictionless track and a couple different cases of what that object could be doing. So a cart on a frictionless track could be just sitting at rest. That means its velocity would be zero, constant zero, so constant velocity. Constant velocity means the acceleration is zero. The only time you have acceleration is if the velocity is changing. If the acceleration is zero, then the net force has to be zero. Sum of the forces, that is not a capital E, that is a Greek letter sigma, which means the summation or sum of the forces, meaning S-U-M, sum, as in add up all the forces. They better all balance out, or in other words, add to zero. So let's check them and see if they do. We have a downward force weight on the cart by the earth. We have an upward force that balances that out, normal force on the cart by the track. So the track is holding up the cart so that it does not crash down through the earth. And so we end up with balance forces, which is our requirement. No left or right forces because there are no objects interacting with the cart that are exerting a force to the left or to the right. And so there aren't any forces on our free body diagram to the left or to the right. Next situation, the cart is getting pushed. So during the time of the push, for there to be a push to the right, the object pushing, so the person's hand or whatever it might be, must be in contact with the cart. We can't have any forces at a distance in this particular case. I can't exert a force on a cart unless I am in contact with the cart. So during the time of the push, the cart goes from being stopped to moving to the right. So that means that the velocity vectors are getting more and more to the right, longer and longer to the right. So the acceleration vector points to the right. You can get acceleration from thinking, what do I have to do to the earlier vector to turn it into the later vector? I'd have to make it longer. So I'd have to pull that handle to the right. Or you can also remember that if I have velocity and acceleration in the same direction, then the object's speeding up. That matches with what we'd expect for during the time of the push. Acceleration vector points to the right. That requires that the sum of the forces is to the right. Free body diagram in this case, we still have weight, we still have normal force, but now there is an additional force to the right because of contact between the cart and the hand. Once there is no more contact between the cart and the hand, this force goes away. Next situation is stop pushing. The object is still moving to the right because it's a frictionless surface. It just keeps going and going. That's what Newton's first law says. Things keep doing what they're already doing, unless we make them stop. So we have a constant velocity to the right. I don't have to do anything to V1 to turn it into V2. So that means there is no delta V. That means there is no acceleration. As long as velocity is not changing, then there's zero acceleration. Zero acceleration doesn't mean the object stopped. It just means that the velocity stays the same. If it's moving to the right, it keeps moving to the right. Sum of the forces has to be zero. So let's check and see if it is. We have still our weight vector. We still have our normal force balancing out the weight that's holding the cart up so it doesn't crash to the floor. There is no longer a force to the right because the hand is no longer in contact with the track. We don't have any force to the left because we said this is a frictionless track, so no friction. Or friction is small enough we can ignore it. Next situation, we need to stop this cart. So the cart is moving to the right. We have to exert a force to the left in order to cause it to come to rest, to come to a stop. So my velocity vectors get shorter and shorter. I'd have to push V1 shorter, meaning to the left, in order to make it into V2. Or remember velocity and acceleration in opposite directions for an object that is slowing down. So acceleration vector points to the left. That requires that we have an unbalanced force to the left. Those acceleration and sum of the forces or net force have to match every single time. Let's check. Weight vector still down, normal force still up. Now there is in fact a force to the left. That's the only way I can stop the object is if I exert a force in the opposite direction that it's going so that it comes to a stop. So acceleration vector has to match the unbalanced force. Another thing to take a look at here is look at the two places, first and third situations where the acceleration was zero. Look at the free body diagrams for those. They are identical. I cannot tell from a free body diagram the velocity of the object. What I can tell is acceleration. First and third both tell me that there is no net force. That requires that there is no acceleration. Doesn't tell me, though, doesn't show me any difference between acceleration is 0 because the object is stopped, or acceleration is 0 because the object is moving at a constant velocity to the right. Free body diagrams tell us about net force, which then tells us about acceleration. They don't tell us about velocity. That weight vector was on every single one of those free body diagrams. Every object that we're going to be interested in has mass, therefore has weight. In other words, there is a force on the object of interest because the Earth is pulling on it. The equation that we use for that is capital W equals mg. So the W in that equation is the weight. That is what is on the free body diagrams. And that has units of newtons because it is a force. We're only allowed to put forces on free body diagrams. So everything that you put on a free body diagram better have units of newtons because that's the unit that we're using for force. Lowercase m is the mass of the object. That has to be in kilograms. Otherwise, you won't end up with the correct unit for weight. The acceleration, g, lowercase g, is the acceleration due to gravity. That is an acceleration, so the unit is meters per second squared. Specifically, the value is 10 meters per second squared, assuming that we are on or near Earth, which is generally a pretty good assumption. We don't use negative 10 here because we just want to know the magnitude or the number part of the weight. We don't want to say the weight is negative 10 newtons. We just want to say the weight is 10 newtons, and then on your free body diagram, you can see that it points down. This graph shows the force, friction force, versus time for an object that was at rest. You had to push on it, get it going, and then moving it at a constant speed. The pink highlighted portion is the static friction portion of that. That shows that static friction can be anything from 0 to very small number to bigger, bigger, bigger number until the object starts moving, and then the friction force actually drops and becomes constant kinetic. The lowercase k there is for kinetic, which means motion. So that is what applies when the object is moving. I like to say constant kinetic so that we remember that that kinetic friction force is a constant for your particular situation. But static friction could be anything from very, very small to much larger, depending on how hard you're pushing on the object. If I barely push on my object sitting on the table, then static friction isn't very big. It's just enough to counteract what the force that I'm pushing with. As I push harder and harder and harder, static friction increases with me to balancing out until finally it can't get any bigger. We've reached maximum static friction, in which case the object starts moving, and then the constant kinetic would apply. We have two equations for this. We have static friction is less than or equal to mu s times the normal force, and then the kinetic friction equation is mu k times the normal force. So we can look at the parallels. They're very, very similar. The top one applies to static. That means not moving. And it has the less than or equal to because, once again, it could be very small. If I'm barely touching the object, friction force doesn't have to be very much to balance me out, or up to much greater value. Make sure we know what the units are. This would apply to both of those equations. The scripty F, or the italics F, is the friction force, and that is a force, so it must be in newtons. The fancy cursive U, really the Greek letter mu, is the coefficient of friction, and that is a unitless number. Incorrect to put a unit with that number. Think of it as just a multiplier, just like the 2 in 2x, if this was math class. The coefficient is that multiplier number, and it's multiplied times the normal force, which is capital N, and that has units of newtons. So if I have a box and I am moving it across a floor that has friction, its free body diagram would have three forces on it. If I just give the box a push and let go, once I let go, there is no force because of me. So if I give the box a push to get it going, but then let go, it will slide across the floor and come to a stop because friction. This free body diagram would have weight because my box has mass, and then the normal force balances that out on the box by the floor. And there is friction in this situation. Friction always opposes the motion. So if the box was sliding to the right as it was coming to a stop, friction opposes that motion. The box was moving, therefore we're talking about kinetic friction and not static. Box is moving, and that would be on the box by the floor. Wanted to clarify here that this normal force that is upward, yes, it balances out the weight, but you can also think of it as that is the force that is pressing the two surfaces together. You can think of that as the force that is pressing the box and the floor together. That is the capital N in the friction equation. That's one of the two factors for friction, is what is the force that is pressing the two surfaces together. More normal force means more friction force, directly proportional. The force that opposes the motion is the force of kinetic friction, which is the left side of that equation. So that's how the force, the kinetic friction force, and the normal force match up with the free body diagram. They are tied together. So quite often you'll need to know what the normal force is in order to calculate friction force. This is how they tie together. The other factor that affects friction is that coefficient of friction. It's a unitless number, and it just depends on what the surfaces are. That would have to be experimentally determined. The coefficient of kinetic friction for ice is different than the coefficient of kinetic friction for carpet or for tile. The bigger the coefficient of friction, the more friction force you would get for the same normal force. So once again, directly proportional. Coefficient of friction is a unitless number, and common mistake is the problem will tell you a coefficient of friction is 0.2. That does not mean that the force is 0.2. That means that mu is 0.2. You can also recognize coefficient of friction numbers because it'll say coefficient. Clue in on the coefficient there, not the word friction. Coefficient is 0.2, for instance, and also because those coefficient of friction numbers are between 0 and 1. So those multiplier numbers, those things that are describing how rough or how smooth the surfaces are. That's really what coefficient of friction is telling you, is how rough or how smooth the surfaces are. They are between 0 and 1. So if you calculated a coefficient of friction and you got negative, you did something wrong. If you calculate coefficient of friction and you get 200, you did something wrong. Coefficient of friction is between 0 and 1. And again, it's telling you how rough or smooth the surfaces are. If you have a particularly smooth surface, like say ice, it'd be a very small number, like 0.1. If you had something like carpet that is has a lot more friction, then they might be much larger, like 0.6 or 0.7, something along those lines. Hope this was helpful, and thank you for listening.